All right, so hi everybody, welcome back. Today we're going to be starting a new chapter. That's chapter 11 of G and Pulley. And the topic here is angular momentum. So let's get into this. Now, to introduce you to the idea of angular momentum, I want to compare this to something that you've seen already, linear momentum, which is a very closely related concept. So remember back in chapter 9, when we first encountered linear momentum, we saw that this is a very useful quantity because, among other things, it's related to force. So remember, we have this result that we derived. The net external force acting on a system is equal to dp dt, where p is the linear momentum of the system. And what we're doing here is we're taking the time derivative of the linear momentum on the right-hand side of that equation. Now, if we have a system where there's no overall external force acting on it, in other words, if the net external force is equal to 0, that immediately implies that dp dt is equal to 0. In other words, when you don't have any external force acting on the system, the linear momentum, p, is not changing over time. In other words, it's conserved. So this is where the whole idea of conservation of linear momentum comes from. So as we're going to see, there's a very similar argument that we're going to make for angular momentum, and we'll build up to that in this lecture. So what is angular momentum in the first place? Well, angular momentum is given by L. It's a vector quantity, and it's basically the rotational equivalent of linear momentum. So it's a measure of how difficult it would be to bring a rotating object to a stop. So if a rotating or a spinning object has a lot of angular momentum, that means it's going to be very difficult to bring it to a stop. So I want to ask you guys a question, and I want to see if you can work this out. By direct comparison to linear momentum, P, remember the formula is P is equal to m times v. That's the linear momentum of an object. What would you guess the formula for the angular momentum of a rotating object is? So think back to chapter 10. We have sort of a rotational analog of mass, a rotational analog of velocity. Based on that stuff, what do you think the formula for angular momentum should end up being? So pause the video, see if you can sort of reason this out, and then we'll go through it together. Okay. So the comparison I want to make here is between linear variables, which are used to describe the translational motion of an object, and then angular variables, which describe rotation. And let's just name a few. For linear variables, we have things like P, which is linear momentum, m, the mass of an object, v, the linear velocity of an object, a, the linear acceleration, and we could list some more, but that's just a few of them. Now for angular variables, we have things like L, that's the angular momentum of an object, I, that's the moment of inertia, omega, that's what we call the angular velocity, alpha, angular acceleration. Again, there are more we could write down, but I'm just trying to give you a sense of what we're talking about here. Now, there's a direct correspondence between some of these. For instance, P and L are just the linear and the angular version of momentum. In a similar way, M and I are very similar types of quantities. They both tell you how resistant an object is to being accelerated. So if an object has a lot of mass, it takes a lot of force to get it to start moving. If an object has a lot of moment of inertia, if I is very large, that's telling you it's going to take a lot of torque to get it to start rotating. So these are similar types of quantities. And V and omega are closely related. V is more or less just telling you how fast something is moving, and omega is telling you how fast something is rotating. And there's a direction to each one of these, of course. Now, just by making that comparison, if P is equal to m times v, we might expect that L should be equal to I times omega. So this sounds at least like a plausible version of the angular momentum of a spinning object. And it turns out that is going to be the correct answer, but there are some subtleties to this, and we're going to build up to this and derive this formula. So let's get into that. All right, so eventually we're going to want to have some kind of formula for the angular momentum of a solid object. So the way that we're going to get there, the way that we're going to build up to that, is by first thinking about a really simple case. What is the angular momentum of just a single particle? If we have a formula for this that we can work with, then we can build up to the angular momentum of a solid object. So that's kind of where we're going with this. Okay, so the angular momentum of a point particle. How does this work? How do we calculate this? Well, we have a particle, its mass is m, and it has a position as well as a linear momentum. Okay, so we have some kind of reference frame or a set of coordinates that we're using to keep track of the motion of this particle. So we have an x-axis going this way, a y-axis going this way. That's our reference frame, okay? Now, the position of the particle is the vector r, which goes from the origin of our coordinate system to the point where the particle is actually located. So that's the vector r for position. Now, the linear momentum p is a vector that points just in whatever direction the particle is moving. Okay, so we have r, and then we have p. The angular momentum L is given by the cross product of r and p. So this is the definition of the angular momentum for a single point particle. L is equal to r cross p. That's how we calculate this. Now, remember how we deal with cross products. A cross product of two vectors gives you another vector. So L itself is a vector, and that means it has a magnitude and it has a direction. So we learned how to deal with cross products back in chapter 10. We can find the direction by using the right-hand rule. So remember how this works. You take the fingers of your right hand and you point them in the direction of the first vector, which is r. And then you curl those fingers in the direction of the second vector, which is p. If you do that, your thumb should be pointing in the direction of L. So let's actually try this out using the picture that we have at the bottom of the slide here. So you point the fingers of your right hand in the direction of R, so they should be pointing up and to the right. And then you curl them in the direction of P, so curl those fingers down and to the right in the direction of P. And now your thumb should be pointing into the page. So that's what I'm showing you here. L is a vector that's going into the page. And by the way, sometimes we show this, a vector going into the page using this symbol. What this should bring to mind is an arrow that's going into the page, and we're looking at the tail of the arrow, like that. Okay, so that's how we deal with the direction. Of course, the magnitude, as we learned back in chapter 10, is you take the magnitude of the first vector, so r, you take the magnitude of the second vector, p, and then you take the sine of the angle between those two vectors, which we'll call theta. Okay, so that's how I calculate the magnitude of the angular momentum of this particle. Now, if we think about it, r is just a distance, so it's going to have units of meters. And p is a linear momentum, so it's going to have units of kilograms times meters per second. So if we put all of that together, the SI unit for angular momentum would be a kilogram times a meter squared per second. Okay, that's how we measure angular momentum. Okay, so next, I want us to think about the angular momentum L of a particle that's moving in a straight line path. So just to give you something to visualize, we have this dashed line representing the straight line path that our particle is taking. This is the particle, and it has, again, a linear momentum p, which is just pointing right along that straight line path. Now, you might be thinking, well, this object is not exactly rotating, it's just moving in a straight line path, so shouldn't it have no angular momentum at all? Well, that's not exactly right. As it turns out, this will still have some angular momentum, and it's going to be important to account for that. And the way we'll see this is just to remember that, again, L is equal to r cross p. This is our vector r, going from the origin of the coordinate system to where our particle is located. The vector p is just pointing along the straight line path that our particle is moving in, so that's vector p. And then if I take the cross product between the two, and if I use the right-hand rule to figure out the direction, I'm going to see that L is pointing out of the page like this. So to show a vector pointing out of the page, often we'll use this symbol right here, which is meant to bring to mind an arrow that's coming towards you, and we're seeing the tip of the arrow as opposed to the tail of the arrow like we saw earlier. Okay, so the magnitude of the particle's angular momentum L is given by the formula L is equal to r times p times sine of theta, where theta is the angle between those two vectors. And the magnitude of p, the magnitude of the particle's linear momentum vector, as we'll remember, is given by m times v. So if I take the mass and multiply the speed of the object, then I get the magnitude of its linear momentum. Okay, and so that can go right here in the previous formula as a substitution. Now, the next thing we can do is we can take the straight line path that the object is moving in, and we can connect it to the origin like this. Okay, and this distance d between the straight line path and the origin is what we call the distance of closest approach. So this would be as close as our particle ever gets to the origin. So that would be the distance of closest approach. Well, to figure out what that distance d is, we can notice that we have a nice right triangle here with an angle theta and then a right angle here. The opposite side to our angle theta is d, and the hypotenuse is r right here. So what we can say is d is equal to r times sine theta, just using, again, the definition of sine for a right triangle. And if we notice that we have r times sine theta in the original formula, and again make this substitution for p, we can see that the magnitude of the angular momentum of this particle is given by m, that's the mass, times v, that's the speed, times d, that's the distance of closest approach. So even though this particle is moving in a straight line, it still has some angular momentum. And that's how we calculate it. So let's just get a little bit of practice using this formula. So let's say we have a particle of mass m, which is equal to 2.75 kilograms, moving in a straight line at a constant speed of 45 meters per second. What is the angular momentum relative to the coordinates that are shown here? Let's give both the magnitude and the direction of that vector L. Now, as a follow-up, if we used a different coordinate system where the axes shown here were moved upwards by 1.5 meters, what would the particle's angular momentum be in that coordinate system? So pause the video, see if you can work this out just using the definitions that we've gone over, and then come back to the video once you think you have your answer. Okay, so we'll start by remembering that L is given by r cross p. It's a cross product of two vectors, which means the result has both a magnitude and a direction. For the direction, of course, we're going to use the right-hand rule. And for the magnitude, there are a couple different ways we can think about it, but how about we use the formula that we just derived? L is equal to m times v times d. Okay, so to sketch out what's going on in this case, we have the x, y, and then the z-axis coming out of the page like this. The particle is up here somewhere, and it's moving to the right. So the vector r would be pointing from the location, from the origin of the coordinates to the location of the particle. So that would be the r vector, and then the p vector would be pointing to the right in the direction that the particle is moving. So if we do r cross p using the right-hand rule, we'd point our fingers of our right hand in the direction of r, and then we curl them in the direction of p. If you do that, you should find that your thumb is pointing into the page, which is the direction of L. So L points into the page, which is the minus z direction. Okay, so how about we calculate the magnitude? L is equal to the mass of the particle, that's 2.75 kilograms, times v, that's the speed, which is 45 meters per second, times d. Remember, d is the distance of closest approach. So we have the particle moving in this straight line path shown here. The distance d is as close as that particle ever gets to the origin. That's the distance shown here. And we're just given that that distance is 1.50 meters. So d is 1.50 meters. If you calculate this, you're going to get 185.6, but we'll keep 3 sig figs. The units are kilograms times meters squared divided by seconds. So that rounds to 186 kilograms meters squared per second. Okay, actually that's just the magnitude. If we wanted to write this as a full-fledged vector, we'd write it as minus 186 kilograms times meters squared per second, k hat to show, again, it's in the minus z direction. Okay, so that's actually the answer. Now, what if we moved the axes? If the axes were moved upwards by 1.50 meters. Well, this is what it would look like now. We'd have the x and y axes like this. And the particle would be moving along this straight line. So it's still moving to the right. But now you notice that the particle actually goes straight through the origin at some point. So at some point along the path, the particle goes through the origin, which means the distance of closest approach is actually 0, and L is equal to mvd. If d is equal to 0, L is equal to 0. So if we use this coordinate system, we'd say there's no angular momentum. So the lesson here is how much angular momentum a particle has depends on the coordinate system you're using. So the next thing that we want to take a look at is how angular momentum is related to torque. So we're going to start with L is equal to r cross p. That's just the definition of angular momentum for a single particle. And we're going to do a derivation starting from there. So the first step in the derivation is to take the time derivative of both sides. So on the left, we have the time derivative of L, and on the right, we have the derivative with respect to time of r cross p. Now we have to be careful with the right-hand side. How am I actually going to evaluate this derivative of r cross p? Well, since we have two terms being multiplied together, I can use the product rule to evaluate that derivative. But since it's a cross product in particular, I have to be careful to not change the order of the terms, because remember, when it comes to a cross product, the order of the terms matters. R cross P is not the same as P cross R. So the idea is I'm going to apply the product rule without changing the order of the terms. I'm always going to keep R first and P second. Okay, So on the left side, we have dl dt. On the right side, okay, the product rule is you take the derivative of the first term multiplied by the second term. So that's going to be dr dt cross p. And then you add to that the first term multiplied by the derivative of the second term. So we're going to have r crossed with dp dt. That's how you evaluate the derivative on the right-hand side. Okay, so we're going to make a number of substitutions next. First, dr dt, that's the time derivative of position. That's just velocity, right? Velocity is the derivative of position with respect to time. Where you see p here, that's the linear momentum, which is mass times velocity, so you can sub that in right there. And then also where you see dp dt right here, that's just the net force acting on the particle. So that's something we derived back in chapter 9, by the way. So when we make all those substitutions, we have dl dt on the right side, on the left side, and then on the right side we have v crossed with mv when we make these substitutions here. And then we add to that r crossed with F, or the net force. So a few things to note about this. The first term is equal to 0, because what we're doing is we're taking the cross product of v with v. When you have two vectors pointing in the exact same direction, the cross product is always going to come out to 0. So if you take the cross product of a vector with itself, you're always going to get 0. So that means the first term is definitely coming out to 0. Now the second term should look kind of familiar. We have r crossed with the sum of all forces, or the net force. Remember, torque is r cross F, okay? So that second term here is actually the net torque acting on our particle. So the result here is this. We have dl dt on one side equaling the sum of all torques on the other side. So the net torque acting on a point particle equals the time rate of change, or the time derivative, of its angular momentum. That's what that is saying. So let's take a look at that result we just derived in kind of a broader context, okay? So I want us to think about Newton's laws of motion. We have the translational version and the rotational version of the laws of motion. And I just want to look at them side by side and see where this result we derived just a second ago fits into this picture. Okay, so remember the first law of motion. It says an object is going to move at constant velocity unless it is acted upon by an unbalanced force. So if you have an object with no overall force acting on it, it's just going to keep moving at a constant velocity. There's also a rotational version of this, which is that a rigid object will rotate at a constant angular velocity unless it is acted upon by an unbalanced torque. So if you have something spinning and there's no overall torque acting on it, then it's just going to continue spinning at that same angular velocity, and that's not going to change. So that's the first law applied to translation and for rotation. Okay, the second law, F equals ma. That's how we're used to seeing this from back in physics 44. But remember, there's another equivalent way to write this equation in terms of momentum. This says the net force is equal to dp dt. Okay, so what about when we're dealing with rotation now? Well, the second law equation is the net torque is equal to I times alpha. And what we just saw, what we just derived, is that there's a momentum formulation of this. We can just as easily write this as the net torque is equal to dl dt. Okay? Now, the third law, just to complete the list, says that when you have two objects interacting, they exert equal and opposite forces on one another. That's the third law for translation. Turns out there is an exactly analogous statement for rotation, which says when two objects interact, they exert equal and opposite torques on each other as well. So that's kind of the big picture as far as the translational and rotational version of Newton's laws. And again, the result we just derived fits in right there in this overall picture. All right, so strictly speaking, everything we've learned about so far only applies to a single particle. So we know how to deal with the angular momentum of a single particle. The next thing we want to tackle is how do we deal with the angular momentum of a system of many different particles? So that's what's next. So the basic problem is this. Instead of just one particle, we want to consider a system of many particles. Now, this can be anything from a huge collection of atoms that are bound together as a solid object, like a spinning wheel or a rolling ball, some kind of solid object like that. Or we could be talking about a group of independently moving objects. Whatever the case may be, we're talking about a system of many different particles. That's all that matters. Okay, so the total angular momentum of a system of particles would simply be the sum over all of the individual angular momentum vectors. So if L is the total angular momentum of our system, well, that would be the angular momentum of the first particle, which would be R1 cross P1, and then add that to the angular momentum of the second particle, which would be R2 cross P2, and then add that to R3 cross P3, and keep doing that until you've included all of the different particles. So again, the basic picture is you have a bunch of different particles. Each one has a position R and a linear momentum P. If you take R cross P, you'll get the angular momentum of that particle. You'll get L. And so if you do that for all the different particles and then add the results together, that's the total angular momentum of the system. So one result that we're going to derive is that the net external torque acting on the system is equal to the time rate of change of that total angular momentum. In other words, the net external torque on the left-hand side is equal to dl dt. That's the time rate of change of the total angular momentum of that system. So actually, let's derive this result right now. Okay, so the first thing we'll note is that for a single particle, we derived this result already. The net torque is equal to dl dt. And of course, if we have a system of n particles, so n is just the number of particles that we have. Okay, this result right here will apply to each one individually. Okay, so for each particle, I have that result which I can apply. So to put this all in one equation, how about we take the net torque acting on particle 1 and the net torque acting on particle 2 and keep going with that until we reach the end. So the net torque acting on particle n. We know that should equal dl1 dt, so the time derivative of particle 1's angular momentum plus the time derivative of particle 2's angular momentum. And we have to keep going with that sum until we reach the last one. So that would be dln dt. Okay, the next thing we can do is take a look at the left side of the equation where we have basically every single torque acting on every single particle being added together. So that's a whole lot to deal with, but in general, we can split this up into internal and external torques. So an internal torque would be a torque from something in the system exerted on something else in the system. An external torque would be coming from the outside. Now, on the other side, we have basically one big time derivative. We can think of this as the time derivative of L1 plus L2 plus, add them all together, the last one is Ln. Okay, So what I have in the square brackets here is the total angular momentum of the system. And on the left side, again, I have external torques and I have internal torques. But the internal torques are going to add to 0. So these will sum to 0 because of Newton's third law. Okay, for any torque that I have there, I'm going to have an equal and opposite torque, which will cancel it out in the sum. So when I add them all together, I'm going to get 0. So the end result is the net external torque on the system is equal to dl total by dt. Again, that's the result that we wanted to derive. That's where it came from. All right, so the next thing we're going to do is a bit of a derivation. And the question I want to answer in this derivation is, how do we calculate the angular momentum of a solid object? We already know that for a single particle, angular momentum L is given by r cross p. But what about for a solid object? What's the formula in that case? Well, that's the point of this derivation, is to show you how we can go from a single particle, where L is equal to r cross p, to a solid object that is composed of many different particles, and we'll get a really simple formula for that angular momentum. So to start, let's just think about a single particle, and let's say it's rotating around the z-axis, like this. Let's say the particle has a mass m. Let's say the rotation is going this way. Now the radius of this circle that the particle is moving in, let's call that r prime. And that's not to be confused with r, which is the vector going from the origin to that point where the particle is located. Now p is the momentum. That's just the mass of the particle times its velocity. All right, so it's a little bit difficult to visualize 3 dimensions on a 2-dimensional drawing like this. So what I'm going to do instead is redraw this, taking the side view, where we're looking into the x-axis. Okay, so imagine you're taking this perspective, you're looking into the x-axis. What does this picture look like now? Well, we're going to have the z-axis going up just like before. The x-axis will be coming out of the page towards you, and the y-axis will be going to the right like this. So that's the new picture. The particle is over here somewhere, its mass is m, and the vector r simply locates where that particle is, so that's the position r. Now the linear momentum p, from this perspective, is going to be going into the page. So there's the vector p. Okay, we have to be kind of careful now. Remember, L is equal to r cross p, right? Well, if we use the right-hand rule to figure out the direction of the L vector, I'm going to point my fingers in the direction of r, and then I'm going to curl those fingers in the direction of p using my right hand. So try this out. Point your fingers of your right hand in the direction of r, and then curl those fingers into the page, which is the direction of p. And you should find that your thumb is now pointing kind of up and to the left, like this. So there's the vector L. Okay, when it comes to the magnitude of L, because we just figured out the direction, remember the magnitude of a cross product is given by the magnitude of the first vector, which is r, times the magnitude of the second vector, which is p, and then the sine of the angle between them, But if we consider the r vector and the p vector shown here, they're actually at a 90-degree angle to each other because the r vector is in the plane of the page and the p vector is going into the page. So they're at a right angle or a 90-degree angle relative to one another. So if we remember that p is just m times v and sine of 90 is just equal to 1, this is the magnitude of the angular momentum of the particle that we're looking at. Okay, so that's the basic picture. Now to add a little bit more detail to this drawing, we'll remember that the radius of the circle that the particle is moving in is r prime. So that would just be the distance between the z-axis and the particle shown there. And let's label this angle right here theta. That's the angle between the r vector and the z-axis. Let's also take the L vector and break it into components. And in particular, I'm going to be interested in this component that goes along the z-axis, which I'll call LZ. So I'll notice that over here, I have the same exact angle theta as before that our L vector makes off of that horizontal line. And then, of course, here I have a right angle. So basically, I have these two different triangles in the problem. One is the r vector, and the other is composed of the L vector. But if I think about sine of the angle theta that's shown in the picture there, it's always equal to the opposite side divided by the hypotenuse. That's the definition of sine. Well, using the triangle at the bottom, the opposite side is going to be r prime. So that's the angle across, or sorry, that's the side across from the angle theta, r prime. The hypotenuse is just r. If I use this triangle over here, okay, then the opposite side is going to be LZ, and the hypotenuse is going to be L, the overall angular momentum. Okay, so I have two results here. One says that LZ is equal to L times sine of theta. The other is that r prime is equal to r times sine of theta. Okay, so here's what we can do next with this. If LZ is equal to the magnitude L times sine theta, well, the magnitude is r times mv, and then we're going to multiply that by sine theta to get the z component, like we just said. And that's the substitution we made. Well, I can rearrange this to say r times sine of theta times mv, and this part right here, r sine theta, is just equal to r prime. So what we have is LZ is equal to m times v times r prime. Okay. The next thing I want to remind you of here is that we have something called a tangential speed for an object moving in a circle. That's given by v equals omega times the radius of the circle we're moving in, which in this case is r prime. Remember, r prime is the radius of the circle that this particle is moving in. So the tangential speed of that particle would be omega times r prime. Okay, so make that substitution here. And then I'm going to have m times omega times r prime multiplied by r prime, or LZ is equal to m times r prime squared times omega. Okay, I want to remind you that the moment of inertia of a single particle is given by m times r squared. This is the moment of inertia of a single particle. So if we go ahead and make that substitution there, we're left with LZ is equal to I times omega. Okay, so of course that result applies to a single particle. So what if we have two particles rotating about the z-axis on opposite sides? So here's what I want you to think about. We have the z-axis, and then here's x, here's y, here's z. So we have two different particles rotating in a circle around the z-axis. So let's say we have m1 over here, m2 over here, and they're rotating this way. So if we take the side view, this is what we'll see. We'll have the z-axis like this, the y-axis like this, and then particle 2 is over here on the right side. Particle 1 is over here on the left side. Now, from this point of view, we're going to see particle 1 moving out of the page towards us. So this is going to be the momentum P1, where particle 2 on the right side is moving into the page. This will be momentum P2 for that particle. Of course, the R vector just points from the origin to where the particle is located, so that's R2. This is R1. And the L vector for particle 2, if we do R cross P, is going up and to the left like this, so this will be L2. For particle number 1, if you do R cross P using the right-hand rule, you're going to see L1. That angular momentum is going up and to the right like this. Okay, so what would be the total angular momentum of those two particles? Well, L total would just be L1 plus L2. And let's actually draw this out. How do we do L1 plus L2? Well, if L1 is pointing up and to the right like this, and L2 is pointing up and to the left like this, this is how we show them being added together, tip to tail, to give you L total, which actually just points straight up. So the point of what I just drew, the point of showing you this, is that everything except for the z components is going to cancel out. Right? Because overall, we're just left with an angular momentum going in the z direction. So therefore, L total is going to be, okay, well, the z component of angular momentum we just found over here is equal to I times omega. So I'm going to have I1 times omega, and that's in the z direction, so let's say k hat. And then I'm going to have I2 times omega. If it's in the z direction, that's also going to multiply k hat. Basically, I1 plus I2, let's call that I total, is multiplying omega times k hat. Okay, so the last thing to realize here is that if we have a symmetric object, we can build it up using pairs of particles on opposite sides of the symmetry axis. So here's what I mean by that. Let's say we have a sphere, and
this axis right here will be the symmetry axis. So for any particle that I pick out, let's say this particle over here on the left side, I know there's a corresponding particle on the right side because, again, it's symmetric, an equal distance away from that symmetry axis. Okay, so then what if we're actually rotating about this axis? In other words, we're rotating this way, and this is our omega vector. Well, this is the situation we've been describing in the derivation, where we have a particle m1 on one side of the axis and another particle m2 on the other, but they're just both rotating around the axis in a circle like this. Well, we know that for those two particles, the angular momentum total is given by the total moment of inertia I times omega. And again, since for any symmetric object, we can build it up using those pairs of particles, we know that overall, the angular momentum is going to be given by I, that's the total moment of inertia for that object, times omega. So L is going to be pointing in the exact same direction as omega in this case. So this result that we derived, it strictly speaking applies to a symmetric object rotating about one of those axes of symmetry.
And so here's the result that we derived. If we have a solid object that is rotating about a symmetry axis, so for example, let's say we have this cone and it's rotating about the z-axis as shown here. We call this a symmetry axis because the object looks exactly the same on either side of the axis. It's perfectly symmetric with respect to that axis. So if that's the case, then the angular momentum of the object, L, and the angular velocity of the object, omega, are going to be pointing in the same exact direction. And furthermore, the angular momentum can be calculated using the formula L is equal to I times omega, so just the moment of inertia I times the angular velocity omega, that gives you the angular momentum L. Now, be careful if you ever use this equation. The angles must be given in radians in order for this to work. But anyway, that's the result that we derived. So L is equal to I times omega, strictly speaking, only applies to objects spinning around a symmetry axis. What if we're dealing with an asymmetric object? Well, in that case, the math gets a little bit more complicated. So let me briefly explain what this is about, but don't worry, we're not going to be using this in Physics 45. This is something that would be covered in a more advanced physics class, but I just want to give you the gist of it. For an asymmetric spinning object, the angular momentum vector L and the angular velocity vector omega will not always be pointing in the same exact direction. In general, if you want to figure out what the relationship between L and omega is, you need to do matrix multiplication. So the idea is we have L, which is a vector with x, y, and z components. If you want to figure out what that is, you have to multiply this 3 by 3 matrix here with omega, which is a vector with x, y, and z components. So it gets a little complicated, and there's a lot of counterintuitive stuff that pops out of this math. But again, we're not going to be doing this in Physics 45. We're going to stick to symmetric objects where the result is a lot more simple. L is equal to I times omega. If you want to learn more about this stuff, take an upper division physics class at the university level. So if you analyze the equation that I showed you on the previous slide, you can get a lot of really interesting and counterintuitive results out of that. And I just want to talk about one of those results. This is called the Zanabekov effect. I'm not sure if I'm pronouncing the name right. This was named after a Russian astronaut who first noticed this effect while he was on board a space station. So this video that I'm going to show you was taken from a space station. So this astronaut is going to take this T-shaped piece and spin it around. And you'll notice that as that piece is spinning through the air, it behaves in a really strange and unexpected way. So did you see that?
as the piece is spinning, it's constantly reorienting itself. So in one moment, it's facing forward, and the next moment, it's facing the other way, then it's facing forward again. It's kind of unstable in its rotation. Okay, it doesn't really stably rotate about this axis. It's constantly flipping back and forth as it rotates about that axis. So that's called the Zanabekoff effect. And if you really want to understand why that's happening, you're going to have to dive into some of that math, which, again, we're not going to cover in this class. It's going to be a topic for an upper division physics course. So if you want to understand why this is happening, keep taking physics through the university level, and you'll eventually get to why this is happening. Now, there's a video link left at the bottom of the slide. You can see this video again, and I'll also learn more about the Zanabekoff effect if you like. I just want to give you a sense here of what sorts of things lie beyond Physics 45. If you keep taking physics, what kinds of things might you start learning about beyond Physics 45? This is one of them. Okay, so that was a little aside. Let's go back to the main topic of the lecture, and let's do an example problem where we calculate the angular momentum of an object using the formulas we derived. So the Earth has a mass of 5.97 times 10 to the 24 kilograms and a radius of 6,370 kilometers. Earth orbits the Sun at an average distance of 149.6 million kilometers. If we treat the Earth as a uniform sphere, let's calculate the angular momentum of the Earth due to its rotation on its axis. So, of course, the Earth rotates on its axis once every day. What is the angular momentum of the Earth due to that motion? And then as a follow-up, let's calculate the angular momentum of the Earth due to its orbit around the Sun. So the Earth orbits the Sun once every year. Let's calculate the angular momentum of the Earth due to that motion as well. And in each case, we're going to give the units as kilograms meters squared per second. And we're going to need to know this formula. The moment of inertia of a solid sphere rotating about its center of mass is given by 2/5 mr squared. Okay, so let's work each one of these out and see what we get. Okay, so when it comes to Earth's rotation on its axis, we have to remember that what we're dealing with is a solid sphere rotating about an axis that goes right through its own center of mass. Something like this. And in this case, the moment of inertia is 2/5 times the mass of the sphere times the radius of the sphere squared. Okay, next, we're going to need to know omega. That's the angular speed of the rotation, which is delta theta over delta t, so the angle it rotates through divided by the time, which in this case is 1 revolution every 1 day. That's how fast Earth spins on its own axis. But we better convert that to radians per second, so we have 2 pi radians per every 1 revolution. Cancel out revolutions. And every 1 day, we have 24 hours. Cancel out days. And every 1 hour, we have 60 minutes. Cancel out hours. And then finally, in every 1 minute, we have 60 seconds. So cancel out minutes. Okay, numerically, this comes out to 7.272 times 10 to the minus 5. And the units we're left with are radians per second. So remember, L is equal to I omega. So the magnitude of L would just be I times the magnitude of omega. That's what we're essentially doing here. So the magnitude of this angular momentum is going to be I, which is 2/5 times m times r squared, like we said, and then just multiply omega. That's what we have. So 2/5 times the mass of the Earth, which is 5.97 10 to the 24 kilograms times the radius squared. Well, the radius is 6,370 kilometers, which is 10 to the 3 meters. So square the R value. And then omega is 7.272, 10 to the minus 5 radians per second. Okay, unit-wise, what we're dealing with is kilograms, meters squared over seconds. Now, radians, remember, is not a proper unit. We can leave that off. Kilograms times meters squared per second is what we're dealing with in terms of the units. And this works out to 7.046, 10 to the 33. We'll keep 3 sig figs on that. 7.05, 10 to the 33 kilograms meters squared per second. So that's how much angular momentum the Earth has as a result of its rotation on its axis. Now, if we look at the orbit around the sun, it's a bit of a different story. Earth's orbit around the sun. So now what we're dealing with is the Earth moving around the sun. And let's call the distance between the Earth and the sun lowercase r, whereas the radius of the Earth is uppercase R. Now, the distance between Earth and the sun is a lot bigger than the radius of the Earth. Okay, the radius of the Earth is about 6,000 kilometers. The distance between Earth and the sun is like 150 million kilometers. So way bigger than the radius of the Earth, which means we can treat the Earth as a point mass that orbits the sun. And in this case, the moment of inertia for a point mass, if you recall, is just mr squared, where r is the distance between that point mass and the axis of rotation. Okay. So, what about omega in this case? Well, omega is going to be not 1 revolution per day, but 1 revolution per year, because it takes 1 year for the Earth to orbit around the sun. So let's convert the units just like we did before. There are 2 pi radians per every 1 revolution. And in every year, how many seconds do we have? Well, let's just do it all in one step. We have 365 days, and then we have 24 hours in a day. Then we have 60 minutes in an hour, and then 60 seconds in a minute. So 365 times 24 times 60 times 60 takes us from years to seconds. So unit-wise, we're left with radians per second. Omega is 1.992, 10 to the minus 7 radians per second. Okay, so L, remember, is I times omega, where I is mr squared times omega. So we have the mass of the Earth, 5.97, 10 to the 24 kilograms, times r, which is the distance between Earth and the sun, 149.6 million kilometers. So a million is 10 to the 6, and then a kilometer is 10 to the 3 meters. And then we better square that as well. And then multiply the omega that we just found, which is 1.992, 10 to the minus 7 radians per second. So if you do the math, you'll get 2.662, 10 to the 40 kilograms meters per second, kilograms meters squared per second, which when we round it works out to 2.66 times 10 to the 40 kilograms times meter squared per second. So again, this is the spin on its own axis. This is the orbit. So there's a whole lot more angular momentum that the Earth has as a result of its orbit compared to just spinning on its axis. That's what we found. Okay, now in this question, we're going to be using the result, the net external torque acting on a system is equal to dl dt. Now in this problem, we have a pulley that consists of a uniform disc, mass capital M, is equal to 2.5 kilograms, and it's mounted on a frictionless axle. A block with mass lowercase m is equal to 1.2 kilograms hangs from a massless string that is wrapped around the rim of the disc. Find the linear acceleration of the falling block in meters per second squared. So this is a problem that we've done already. We did this one back in the chapter 10 lecture. I want us to revisit it and try to work it out again, but this time using this formula. So pause the video, see if you can work this out, and then come back to it and we'll go through it together. Okay, so in this problem, we're using the result that we derived earlier. The net external torque acting on a system is equal to dl dt, where L is the total angular momentum of the system. So if we're going to use that, we better define what our system is. So for this problem, let's call the system the disk and the block together. Okay, so there's the disk, mass capital M. The axis of rotation goes right through the center of the disk, which has a radius r. We have a string hanging off the end of the disk, which is attached to the block, mass m, lowercase m. Okay, so to indicate how fast the block is falling, we'll use v for that. And to indicate how fast the disk is rotating, we'll use omega for that as well. And then we'll show the coordinates with the x, y axes in the plane of the page and the z-axis coming out of the page like this. Okay, so we better think about what the external torques acting on the system are. And it turns out there's only one, which is only the torque due to gravity acting on the hanging mass. So this is the force that I'm talking about, Fg, acting on the hanging mass, pointing downwards. Now remember, if we only have one torque to think about, torque is given by R cross F, so we have R cross Fg. And by the way, this is the only torque because we have no friction or anything else that would cause the disk to start rotating. So the R vector points from the axis of rotation to the point where the force is applied. So that's the R vector shown there. Now, just by the right-hand rule, we can figure out the direction of the torque. You point the fingers of your right hand in the direction of R, and then you curl them in the direction of the force. Your thumb should be pointing out of the page in the positive z direction. So the torque is out of the page, which means it gets a positive sign. And then k hat is going to indicate we're in the z direction. But remember, as far as the magnitude of the torque goes, this can be written as r perpendicular times the force, where r perpendicular is the component of that r vector that is perpendicular to the force. In this case, that would simply be the radius of the disk. So capital R goes there. The force of gravity is little m times g, and then k hat. So positive capital R times little mg times k hat. That's the net external torque acting on the system. That's the left-hand side of the equation that we started with. Okay, next, let's think about the total angular momentum of the system. Well, in this case, we have two parts. We have the angular momentum of the disk and the angular momentum of the block. We need to account for both parts. Now, for the angular momentum of the disk, we can use the result I times omega, because we're dealing with here a solid object rotating about a symmetry axis. Okay, so this formula will apply. Also, we'll note that it's in the z direction, in the positive z direction. If you curl your fingers in the direction that the disk is rotating, which would be counterclockwise, your thumb should be pointing out of the page. That's the right-hand rule telling us that this is in the positive z direction. As for the angular momentum of the block, we can use mvd, because this is a mass moving in a straight line. So earlier in the lecture, we found that for a mass moving in a straight line, you can write the angular momentum as m times v times d. And by the way, this is also in the z direction. Okay, so let's make a couple substitutions into that. First, I is equal to 1/2 times big M times big R squared. That's a uniform disk. That's the moment of inertia. We also have V equals omega R. That's the no slip condition, which will give us omega is equal to V divided by R, like that. Also, D is equal to R. What does that even mean? Remember, D is the distance of closest approach. Okay, so if we think about this hanging block moving in the straight line that it's moving in, the closest it ever gets to the axis of rotation is just the radius of the disk, okay? Okay, so the total angular momentum L, therefore, is given by I, which is 1/2 big M big R squared, times omega, which is V over big R, times k hat. And then we have M times V times D, which is just the radius of the disk, big R, times k hat. So we'll simplify this by canceling out one factor of R. And then we'll notice that we have a common factor in both terms of V times big R times k hat. Multiplying that, we have 1/2 times big M plus little m. So the derivative with respect to time of that total angular momentum, well, that's going to be the derivative with respect to time of 1/2 big M plus little m times V times R times k hat. And we can always pull out constants when we do a derivative. So a number of things are constant here. We have first 1/2 big M plus little m. We have the radius of the disk, and also k hat. These are all constants. The only thing left that we actually need to take a derivative of is V, we're just left with dv dt, which, by the way, that's the acceleration of the hanging mass. So we can call that A. Okay. So not only do we have the left side of the original equation, which is the net external torque, we also have the right side, which is dl dt. So let's put it all together. The net external torque is equal to dl dt. For the net external torque, we have r little mg k hat. For dl dt, we have a half big M plus little m times r times a times k hat. So we worked both of those out. Now we set them equal. R cancels out, k cancels out, and a, the acceleration that we're looking for, is mg divided by m over 2 plus little m. That's what we get when we solve for a. So now we can plug in the known values. Little m on top is 1.2 kilograms times g is 9.8 meters per second squared. Divide by 2.5 kilograms over 2 plus 1.2 kilograms. Now, if you calculate that, it'll come out to 4.8 meters per second squared. So again, that's a problem we've seen before. We've already worked this one out back in chapter 10. This is just a different way of doing it, and you get the same answer. Okay, so with that said, now we can talk about conservation of angular momentum. Let's get into this. So remember the result we derived. It says the net external torque acting on a system is equal to dl dt, where L is the total angular momentum of that system. This is referring to a time derivative or a time rate of change of angular momentum. And if you think about what this is telling us, it's telling us the only way that L is going to be changing is if you have some kind of external torque, some kind of outside torque acting on the system. So what if you don't have that? What if there's no external torque acting on the system overall? In other words, if the left-hand side is equal to 0, net external torque is equal to 0, well, of course, that immediately implies that the right-hand side is equal to 0, dl dt is equal to 0. What that's saying is L is not changing over time. The time rate of change of L is equal to 0, which means L is not changing at all. One way you could say that is L initial equals L final. Doesn't matter when you look at the system, it's going to have the same angular momentum in the initial state and in the final state. Or that's the law of conservation of angular momentum in a nutshell. If there is 0 net external torque acting on a system, the total angular momentum of that system is conserved. That's the law of conservation of angular momentum, okay? And usually, the way we're going to use this is to look at a system, verify that there aren't any outside torques, and then we can say L initial is equal to L final. Okay, so let's take a look at an example where we can actually put this idea to use. So we have two guys standing on a sheet of ice, and let's just assume that the ice is perfectly frictionless, so there's no friction whatsoever. Now this guy is holding a beam horizontally like this, and initially he's just at rest. But this guy slides to the left towards the beam and then grabs the end of it. So what happens after he grabs the end of the beam? Let's take a look. So let's see it one more time. Okay, so clearly what's happening here is at the end of this motion, they're rotating, but they're also translating at the same time. So the idea behind this problem is we're going to figure out how fast they're rotating and how fast they're sliding off to the left after the end of the beam is grabbed. So here's the example. We have two guys of equal mass standing on a flat sheet of frictionless ice. Guy number one is standing still, holding a beam by its end. The beam has a length of 2.50 meters and it has negligible mass. Guy number two approaches at a speed of 3.80 meters per second and grabs the other end of the beam. After that, they move off together. What is the final linear speed of their center of mass in meters per second? And what is the final angular speed of their rotation in radians per second? So as we do this problem, we're going to treat each guy as a point mass. So let's work this out. Okay, so we'll start by defining our system. Let's say for our purposes, the system will be the two guys plus the beam. Now, what does the system look like initially? We have one guy moving to the left at some velocity, we'll call it V0, towards the end of the beam. And at the other end, you have another guy with mass m. They have the same mass, so we'll use the same variable m for both of them. In the final state, now they're both hanging on to opposite ends of the beam. And that beam is now rotating at some rate. Let's call that omega. But at the same time, the center of mass of the system is moving, and we'll call that velocity VCM. Okay, so during this motion, there's no overall external force acting on the system. And there's also no overall external torque. So that implies two different things. The fact that we have no overall external torque means angular momentum is conserved. But also, since we have no overall external force, linear momentum is going to be conserved as well. Okay. So we have two equations to work with. One is for linear momentum. This says P initial is equal to P final. Now let's use the picture that we drew to guide us with this equation. Initially, only one of the two guys has any momentum, and it's going to be given by m times v0. In the final state, well, they're basically moving together as a single mass. Let's call that 2 times m, with some velocity vcm. So that would be the final linear momentum of the system. Now, we can cancel out that mass and then solve for VCM, which would just be a half of V0. So the idea is we've basically doubled the amount of mass that's moving to the left. So we're going to have to cut the velocity in half. Okay, so that's pretty simple. V0 is just minus 3.80 meters per second I hat, just to indicate that we're moving to the left in this coordinate system where x goes to the right and z is coming out of the page like this. That's the coordinate system we're thinking of. And so a half of that is minus 1.90 meters per second I hat. So that's the final velocity of the center of mass of the system. Okay, if we now do angular momentum, we have L initial equals L final for this system here. Okay, so initially we just have a mass that's moving in a straight line. So this is the straight line path we're talking about. By the way, this is the axis that we end up rotating about. It's right in the middle of the beam. So the distance of closest approach is half the length of the beam, shown there. So since initially all we have is a mass moving in a straight line, angular momentum is given by m times v times d, and in particular the speed is v0, the initial speed. The direction, by the way, if you use the right-hand rule, is the positive z direction. So this is how we write the initial angular momentum of the system, because again, we just have a mass moving in a straight line. Okay, now the final angular momentum. Well, we can write this as I times omega because we basically have a rotating object rotating about a symmetry axis. And again, it's going to be in the positive z direction if you do the right-hand rule on that one. So again, this is the formula we use for an object rotating about a symmetry axis. And okay, a couple things we know. First of all, d, as we said earlier, is L over 2. That's the distance of closest approach. Okay, also, what's the moment of inertia at the end of this process? Well, again, we basically have a point mass here and another point mass here rotating about this center point. And we know that for an individual point mass, mr squared gives us the moment of inertia, where r is the distance from the axis of rotation. But we have two, so it's going to be mr squared plus mr squared, or 2mr squared, where r is half the length of the beam. So that would be 2 times m times L over 2 squared. And overall we have 1/2 times m times L squared. Okay, so let's go back to that angular momentum equation. We have m times v0 times the distance of closest approach, which is L over 2. That's equal to I, which is 1/2 times m times L squared times omega. Okay, well, we want to solve for omega here. And actually, that's not too bad because we can cancel out m. We can cancel out that factor of 2 there. And we can cancel out one of the factors of L. So at the end of this, we just have v0 over L. That's what omega is. So omega is v0, which is 3.8 meters per second, divided by L, which is 2.50 meters. And this comes out in radians per second as 1.52 radians per second. So at the end, their center of mass moves to the left at 1.90 meters per second, and they spin around their center of mass at 1.52 radians per second. That's how you do this one. And so that's going to be it for this video. We'll end it here. I'll see you in the next one where we'll wrap up chapter 11 and finish up all this content on angular momentum. So until then, be safe, be healthy out there. See you in the next one.